Hello everyone and welcome back. If you have a question or two, now is a good time to ask. We have a couple of minutes before class. I wish there was a math history course. Me too. In fact, I once took a class, the stats class that some of you have probably taken or are taking. Professor was Roger Fischler, who basically every class he would tell us a math history story. In fact, he had written a book about the history of mathematics, so every class, if you got nothing else from it, you got to at least hear a nice story. Is the final exam multiple choice, since the practice problem posted isn't multiple choice? Yes, the final exam is multiple choice, and the practice problems are deliberately not multiple choice. The reason for that is that I want you to think about those problems when you're studying, and think about how they would be asked as a multiple choice question, which if you do means that you'll have to sort of really understand what could and couldn't be asked. That'll get you to think more about the question that is actually asked there, and I think that's actually more helpful than just giving you one example of a multiple choice question that corresponds to that particular practice problem. Like if you look at a practice problem and you have some idea how to answer it, but you have no idea how you could even ask this as a multiple choice question, then that's probably an indicator that you don't really understand that topic so well. Okay, so welcome to our last lecture. So there won't be lectures next week. It's a good time for you guys to study. We are ahead of schedule for a couple of reasons. One of them is that we actually got an extra lecture this semester. This strange thing happens if you happen to have class on Wednesday and Friday, then in that first week you get to have 2 lectures and nobody else does. So we've got this extra lecture, and also because of this whole online business, I didn't do the typical midterm review lecture that I would do live. I just had you guys review on your own. So this is it. Will I have office hours next week? Yes, and I think I'll actually be able to attend my full 2 hours of office hours this coming week, this coming Tuesday. The last few weeks, strange meetings keep coming up, and I'm forced to attend those, unfortunately. So I either haven't had office hours or had very shortened ones. But on Tuesday, I'll have my full 2 hours of office hours. Okay. Yeah, so the last topic in this course is kind of a warm-up or a setup for a bunch of other things. And it's really just an introduction to the type of issues that we're looking at. And it's about data structures that are fast for external memory. So these days you hear a lot about big data, data science, all these things. What does that mean, really? Well, it could mean many things. In fact, it's gotten used so much nowadays that it's pretty meaningless, actually. But big data typically refers to data that doesn't fit in your computer's RAM. So let's say it doesn't fit in the 16 or 8 gigabytes of RAM that your computer has. So that means it has to be stored somewhere else. And what kind of storage does your computer have other than RAM? Well, computer has a hard disk drive as well, or a solid state disk drive. I'll just call it a hard disk, but when I say hard disk, I could mean a spinning platter of rust, like a traditional hard disk, but more likely your computer has a solid state disk drive in it. And while this thing is, its size is measured in maybe tens of gigabytes, maybe 16 gigabytes, maybe even 32 if you've got a real powerful workstation. This thing is measured, its size is measured in the hundreds of gigabytes or even the terabytes. So you can easily, you can go to Costco today and buy yourself a 4 terabyte hard drive if you want. And so that's about 4,000 gigabytes. So a lot more space available here than you have RAM. And so that's where, if you end up having more data than you can store on RAM, that's where it lives. But it's not the only option. There's sort of another kind of external memory. If you run out of space here, or maybe you just don't have everything here, you may be storing stuff off in the, I don't know, what they call the cloud these days. So the cloud really means someone else's computer, and someone else's computer that's physically probably far away from you, which means that you have to go over the network, and it's probably the internet that you're going to use to get to stuff there. So what are the properties of these things? Well, if you look at RAM and hard disk drives, one of them is a lot faster than the other. RAM is much faster than a hard disk. So for a solid state drive, RAM is probably about 2,000 times faster. So if I say I want this byte from RAM, that's about 2,000 times faster than asking for this byte on the solid state drive. So that's significantly faster. And if you have to go off to the internet and go over a network to get your data, and there's a specific byte on the hard disk attached to the AWS server that you have, then the factor is enormous, right? It's not just a few thousand, it's going to be, I don't know, 1,000,000 times slower. And that's not even necessarily an exaggeration. Yeah, so a solid state drive is about 1,000 times slower. If you have an old spinning chunk of rust like this, or you decided to go for a big backup drive that still spins, it's about maybe 100,000 times slower than RAM. So you've done some implementations and assignments where you had to do stuff that did many operations, and you saw that you can fairly quickly come up with tests that take 5 seconds or so. I mean, that's typically what the server runs a test that takes in that range. And that's a data structure that lives in RAM. If that thing was living on one of these things, well, then it would be 1,000 times slower or 2,000 times slower. So 5,000 or 10,000 seconds. So it's slow. And this would be unbelievably slow. All right. But that's not the whole story. So if that was all of it, then you'd say, okay, well, it's slower, but what can you do? Accessing a byte here is 1,000 times slower than accessing a byte here. Well, what you can do is make use of the fact, I mean, this has been known for a while, and the internet, or things, the network, things attached to the network, and hard disks have a property that's supposed to help you with this fact that they're so much slower than RAM. It's that if I go, let's say, to my hard disk, and I say, okay, I need this byte of data off my hard disk at this location in my hard disk, well, what it will give me back is not just this byte of data, but it'll give me back a whole block of data. Okay? So even though maybe I'm only interested in one byte, what it gives me is a lot of bytes, and that could be 4,000 bytes is a sort of common hard disk size. So you ask for one thing, but what actually comes back is 4,000 things. And why is that? Well, just the interfaces were designed that way because of this problem. If you had to read data bytes off here one at a time, it would be super slow. But if this thing is 1,000 times slower, but you can read 4,000 bytes at a time, actually that's not slower. In fact, that seems like it's faster. The only issue is you don't get to specify any set of 4,000 bytes to read off here. They all have to be living in one block. So that's a feature that's common to all of these sort of external memory things. Same thing with the internet. There are typical packet sizes on networks. 1.5K is a common one. So when you go and ask for something off a server and it has to send it to you, it doesn't just send one byte. In fact, for the same cost as sending one byte, it can send you 1,500 bytes or so. All right. And so the idea is that if you know this, then maybe you can design data structures that take advantage of this. So if my data is so big that it has to live on a disk like this, then maybe what I can do is organize the data so that all the stuff that I need to do a search or to add or remove something only requires accessing a small number of blocks. So it may need lots of bytes or lots of little pieces of data, but those live in a small number of blocks, which I can get quickly. So that's the idea behind the external memory model, and there you can just think of some abstraction where you have a thing called a block store. And what is a block store? A block store is just a way of managing interactions with either the network or with the hard disk, and you can ask it to, for instance, give you a new block. And you can get a block, so a particular block. Let's say the blocks are numbered 0, 1, 2, 3. So when you say, give me a new block, it gives you the index of the block. And when you have such an index, you can then later go back and say, get that block. You can also set the value of a block, right? So if I give you, so the typical sort of thing is you use this to get a block off the disk. So there's a block of data living in RAM now. You do some stuff to that block, and then you maybe say, okay, now put it back on the disk. So I changed the contents of that thing, now write it back to the disk. And that's your interactions with the disk. And every time you do this, you get back a block that has some particular size. We'll call it, we'll double use this term, blocks of size some number b. All right. So that's the sort of model. And what you would like is to make a data structure that's fast, so like all the ones we've seen before, but also in addition to being fast, the number of sort of these things that it does should be small. So we're sort of counting two different things. You know, how much computation, all the things we normally count when we count running time. And then separately, we also want to count the number of blocks that you access. So sort of two things. There is running time and the number of blocks accessed. You typically say that those two operations, read or write, those are IOs, input outputs to the hard disk or whatever your external memory is. You count those separately, and you like both of those things to be small. Okay. All right. And we're going to look today at what is probably the fundamental data structure for managing these sort of storing lots of data in an external memory in a block way like this. And it's called a B tree. And for instance, you interact probably with B trees every day. A lot of file systems, computer file systems, are basically implemented as B trees on disks. Okay? So the way your computer navigates the file system, the way it knows where the contents of a file are, that stuff is all laid out on a B tree on your computer's hard disk. So it all sounds sort of weird and maybe abstract now, but the good news is we've actually seen B trees already. So let's define what a B tree is. So B trees. So it's a tree where all the leaves have the same depth. And all right, so the root has at least 2 and at most 2 times B children. And each non-root, non-leaf has at least B and at most 2B children. And what is this number b here? Well, this number b is chosen so that so if you think about this, that means, well, it looks like then the nodes can store up to 2b, they can have 2b children, so that means the node has to have something like 2b pointers coming out of it. But those pointers are not really pointers, they're just the names of blocks that are stored on your disk somewhere. And it should also be able to, well, what's going to go inside these nodes? There's going to be some keys as well. And this guy here, if he has at least 2 children and at most 2b children, that means he has at least 1 key, so 1 value, and at most 2b minus 1 keys. And this one has at least, if it has b children, it has b minus 1 keys, and if it goes all the way up to 2b, and at most 2b minus 1. So the picture looks something like this. You have a root that has some children, at least 2 of them, and you have other nodes that are not the root, but they're not leaves, and they have something between b and 2b children. So let's do, this one has 3, maybe this one has 1, 2, 3, 4, 5. And actually I'll stop there because it's going to get big quickly. And you know, this then satisfies the definition of a B tree for, in this case, if I take B equals 6, then yes. So the root only needs to have at least 2, and it certainly has less than or equal to 6. Sorry, B equals 3. B equals 3, so 2B equals 6. The root is okay. It has certainly doesn't have more than 6 children, and the root only needs to have at least 2. This one has at least 3 children and not more than 6. This one has at least 3 and not more than 6. It has 5 children. So that's the idea. And even at the leaves, so the problem with drawing these on the board is that even for small values of b, like 3, this thing gets out of hand super quickly. So this is the number of keys there, this is the number of keys there, and at the leaves, they have no children, of course, because they're leaves. Leaves store at least b minus 1 keys, and at most 2b minus 1. All right, so you can really think of the nodes here, they really consist of, you can imagine, a couple of arrays. One of them stores keys, and another one stores pointers. So, you know, this could be the root node with its 2 children. There's some value stored here. I don't know, I'm going to write 20. Then this node here. There's some stuff stored here. In my previous example, this thing had 3 children, so that means it would store 2 values. Maybe they're 5 and 10. And then each of those things also stores a bunch of stuff. This is stuff less than 5. In here, this is between 5 and 10. And this is stuff that is between 10 and can't be bigger than 20. And then over here, we had a monster that had, I think it had 5 children. 2, 3, 4, 5. And maybe the keys it stored were something like 100, 200, 300, 400, and stuff in here between 20 and 100, stuff in here between 100 and 200, and so on. And finally, all the stuff that's bigger than 400. And we've seen this already. In fact, the 2-4 trees that we talked about when we were looking at red-black trees, those are just B trees with B equals 2. Right? Remember, 2-4 trees, every node has at least 2 children, and at most 4 children. All the leaves live at the same level. So that's exactly the same definition. And B equals 2 is special because then there's nothing even special about the root, about the conditions on the number of children. All right. So if these are the rules, then well, the sort of first natural question to ask is, if I store n things in one of these B trees, what's the height of the B tree? How big can the height get? And for that we can do actually what we did with 2-4 trees, which is just to count the number of, let's say, keys that you must store. So actually, maybe we'll count the number of nodes, and we'll see what that gives. So how many nodes are there at depth 0? Well, there's going to be one of them. It's the root. How many nodes are there at depth 1? Well, we said that the root has to have at least 2 children. So at depth 1, we have to have at least 2 nodes. But what about depth 3? Well, that's where things really start to blow up, because each of these 2 nodes here has to have at least B children. So that means we get 2 times B. And if we go another level down, we get 2 times B squared. And in general, if we go to the last level, so the exponent here, this is depth 1. So this would be 2 times B to the height minus 1. And, well, a really silly thing to say is, well, the number of nodes is not more than n. It's not more than the number of keys. That's a really silly thing to say. So that means if I have already this many nodes at the bottom level, that number is not more than n. So that's like saying 2 times b to the h minus 1 is less than or equal to n. If you take logs on both sides, you get a log n on this side, and on this side you get a h minus 1 times the log of 2b, that is the same thing as we take a, oh no, we'll leave that. Divide both sides by log of 2b. You get h minus 1 is less than the log n over log 2b. So h is less than log n over log 2b plus 1. And this log, the ratio of one log divided by another, we usually have a nice way of writing that. That's just the log base 2b logarithm of n plus 1. So it's worth pausing for a second and seeing what does this number look like for some typical values. Well, for, let's say you're storing something like integers, and you have a disk, a block size of 4096 on your hard disk. So when you store, I mean, you've got to store, each node has to store its keys, so those are integers, and it also has to store its indexes, the numbers of the blocks of its children. And if you work it out, you'll realize that you can fairly easily squeeze 256 keys into a block. Okay. So that gives you a value of b that is 256. So that's 2 to the 256 is 2 to the 8. And well, okay, so this is like log base. Well, if b is 256, 2b is 512. Log base 512 of n, and you know that's log base 2 to the 9 of n. And so, you know, what does that mean for big values of n? Well, if I take n is equal to 1 billion, for example, that's not actually a huge value of n, then 1 billion is like 2 to the 30, and this is log base 2 to the 9 of 2 to the 30 is a little bit bigger than 2, but it's less than 3. So that means the height of the tree, if I store 1 billion elements, is going to be less than 3. If this is, those are if those are my parameters. Okay? And if I want to store, you know, but if I don't want to store 1 billion, but I want to store 1 trillion, so 1,000 billion, well, then actually the height is going to jump a little bit. So 1 trillion is like 2 to the 30, so plus times 1,000, that's like 2 to the 40. So 40 over 9 is more than 4, but less than 5. Okay? So the height of the tree is going to be not more than 5. So I can store 1 trillion things in one of these B trees, and I'll get a tree of height less than 5. Okay, good. So let's just write that down and just say that the height of a B tree is, I'll be sloppy about it and just say it's on the order of log base b of n. So a few things about B trees. So that's the the definition of them. There's one thing you have to be a little bit careful of, which is always we have talked about all of our trees by saying that, in fact, when we define binary trees, which is the first time we started talking about trees in this course, we said a node as a fundamental thing. It has a left child, it has a right child, pointers to those two things, and it has a pointer to its parent. In B trees, you do not have a pointer to your parent. Okay? And it's not just to save a little bit of space. There's actually a really important reason for it. So you don't have these parent pointers. That makes some things a little bit more complicated. It also means that probably the easiest way to do things on B trees is with recursion, or if you don't like recursion, some explicit stack. But recursion is not so dangerous on B trees, right? Because the height is proportional to log base B of n. So the depth of recursion is going to be log base B of n. And we just saw that even if n is a trillion, then in sort of a typical setup, that means the depth of recursion is 5. So it's not, you don't have to worry about stack overflow if you use recursion to traverse B trees, because the height is really, really, really low. All right. So let's stick, just for the examples we're going to teach now, let's stick with b equals 3 and 2b equals 6. So we want to be able to do the 3 fundamental operations, which are find, add, and remove. So the 3 basic sorted set operations. And we would like to know the running time of these operations, as well as count the number of IOs. Let's look at the find operation. So how does it work? Well, again, it's hard to work with such small pictures, but I mean it works the way we think it does. It starts at the root. Okay. At the root is an array of keys. Okay. There is at least 2 of them in the array, so at least there's at least 1 in the array, and there's at most 2b minus 1 keys in that array. So you can think of the array has some number of things in here. There's at least 1, and the length of the array is 2b minus 1, and it could even be full, but in general it has at least 1 and then some stuff. So I need to decide from the root, if I'm trying to find the value x, which child should I go to next? So I've got this big array here. This is a small one, but this is an example of what the root could look like. The nice thing about this array is the keys that are in it are in sorted order. And when I'm looking for x, what I want to do is either find x in this node, so in the root node where I'm starting, or whatever node I happen to be at this step in the search. And if I don't find it, then I want to know which child to go to. So for instance, if I was searching for 305, from here, well, 305 is bigger than the only key here, so it should go to the right child. Here, 305 is between 300 and 400, so it should go to this child, and then I have to look in this node to see if 305 is in there. So how long does that take? Well, this is an array of length 2b minus 1. there's, what's in this array? Well, there's a bunch of things that are in sorted order, and then there's a bunch of spaces that are not used. So you can think of putting some special value in those spaces to indicate that they're not used. And if you do that, then you'll realize actually you can use binary search to search this array, even though there's spaces that are not used, because you would just do something like this. You go to the middle element of the array. You're looking for 305. 305 is bigger than that middle element, so you should go looking in the second half. Now there's a choice, but maybe you go looking here, and you can't compare 305 to this because there's nothing there. There's a null or something there. But the fact that this is null means that you've gone too far. So you go to the first half. So in general, there's a part of the array, and in fact it's actually nearly half of it that has real data in it, and then there's a part that's null, but you can still do binary search on that. If you ever see null, it means you've gone too far, and you should go to the first half, and you end up with some search like this. And you do that just right, and you find either the thing you're looking for in the array, in which case you're done, you've found it, you can return it, or you see that it's between two values in the array, in which case you follow the pointer to that child, so that means you go to the node down here, or it's bigger than everything in the array, in which case you go to the last child, or it's smaller than everything in the array, in which case you go to the first child. How long does that take? Well, so a search goes through a bunch of nodes until it eventually finds the thing or realizes that it's not there. How many nodes does it go through? Well, that's the height of t. And it does a binary search within the node to find the right child to go to. The node has size 2b minus 1 at most. Well, it does binary search on an array of length 2b minus 1. So that means it takes O of log b time to search in each node. Okay? So the search time is the height of t times log of b. But the height of t is at most log base b of n, and log base b of n is just log n divided by log b. So the b in the base here cancels with this thing, and you just get O of log n. So the running time for find is O of log n, just like in our, just like all the other nice sorted set data structures we've seen. Skip lists, red-black trees, scapegoat trees, treeps, all of those things. So the running time of these things, even though they look more complicated, for a find is not any slower. And the trick really is the extra work that it takes to search a node because it's big is made up for by the fact that the height of the tree is smaller by the same factor. So it takes log n time to look in a node instead of just constant time, but the height of the tree is also decreased by a factor of log n. All right, so the running time for that is O of log n, but what about the number of IOs? How many blocks do I have to access? Well, we've chosen B so that each of these nodes fits into one memory block on our hard disk. And so the number of nodes we access is just the height of the tree, or the height of the tree plus 1. And the height of the tree is only log base B of n. So the running time is O of log n, but the number of IOs is only log base b of n. So again, thinking about the setup we had before, yeah, so maybe memory is a 1,000 times faster than our hard disk, and so this is not too bad. So this is like log n over log b. So b we said was 8 or 9 or 10 for certain things. So the over the naive algorithm, which would be just to implement a binary tree and on the hard disk and not worry about how things are set up, this saves about a factor of 8 or 9 or 10 in the number of IOs. And actually, you can't really save any more than that. Okay, good. Now, so that's the find operation. And what about something like the add operation? So again, we've kind of seen how the add operation works because we've seen it for 2 4 trees. So the add operation of this B tree, you want to add the value x, and first thing you do is you go follow the search path for x in this B tree. If you find it along the way, then you don't have to do anything. X is already there. You don't need to add it. So the interesting thing happens when you don't find it. You get to some leaf. If you looked what's going on inside that leaf, well, that leaf has an array of things in it. And let's stick with b equals 3 again. So this array has length 5, 1, 2, 3, 4, 5. So 2b minus 1. And x fits neatly in between two things in that array in general. Or it's smaller than everything, or it's bigger than everything. So maybe you have a couple of things that are less than x, then maybe a couple of things that are bigger than x. And well, all you have to do then is shift these over and put x where it needs to go. So just insert x into the correct sorted order in this array. And that's great. There's only one problem, and you see it already showing up here, or it's about to show up here. What if this array is already full? Like, for example, if the next thing I try and do is add y, which wants to go right beside x, then when I do that shifting, there's one element that is there that I don't have room for anymore. Okay. So that I need to fix, and I have a picture of how you fix that here. So here's an example. Maybe this was the bottom, let's say the bottom node. It was, before I added anything, it was already full. So it had its 5 values. Then I tried to add something that required this. I added here, I shifted, and now one of the values fell out. So that's called an overflow. And when that happens, you do a split. And it's worth going through this carefully. So this number of keys before was 2b minus 1. And if the node actually had children, that means that before this it had actually 2b children, the maximum number of children it could have. And now I added this node, this extra value, and now there's 2b, which is too much. So how do I fix that? Well, I'm going to split this node into two. And it's going to look like this. So I have 2b keys. That's the total number of keys that I have here. The 2b minus 1 that were there before, and the extra one that I just added. So I split this into two. One side will get b minus 1 keys. The other side will get b keys. And then you think, oh, but wait a minute, b minus 1 plus b doesn't add up to 2b. Where did the extra key go? Well, if I'm splitting this into two, that means this node, this node in general has a parent, and its parent is going to have an extra child now, which means it needs to have an extra key. So that middle key, in this case it's 4 in this example, ends up getting inserted up into the parent. So I want to add something to this node. It makes it overflow. I split it into two, and that makes me put one thing up into the parent. And when I do that split into two, I get one node having b minus 1 children, and the other one having b children. Or not children, but keys. And now, of course, what just happened is I had a problem down here, I fixed it, but I may have created a problem up in the parent. Because who knows how many keys were already stored in the parent before that. Maybe the parent was already storing b minus 1 keys, in which case it's going to overflow, and we have to then split the parent. But you can do that, and at the final step, maybe you end up having to do this whole bunch of split, 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 and maybe even at the final step you end up you had a root which gets split into two. So this is the root. It gets split into these two things. So you can't have two roots, and so what you do then is you create another root. And that key that these things shot up ends up being the one key that lives in this new root. So the insertion algorithm is simple. You find the leaf where you want to add this thing, add it to that leaf. If it causes an overflow, you split it, which means then you have to add a new key to the parent. If that causes an overflow, you split it, and so on. And if that goes all the way up to the root, then you get a new root. The height of your tree increases, and that's the way it sort of had to happen, because this rule says all the leaves have the same depth, and the only way then to increase the height is by sticking a new root on top. You can't just push down one leaf at a time, or attach things to leaves. All right. All right, so that's the find operation, and so, or not the find, the add operation. So this find was log n and log base b of n, but this add operation, there's maybe a bit more going on. Let's see. Well, first thing is the search. That's going to take log n time. That's the same thing as the find operation. Then I take this new key and I insert it into this array, this leaf here. Okay? But this leaf is an array, and that's not efficient to insert into. So, I mean, that really is, you know, just like we learned about lists, array lists at the beginning. If you want to insert at a specific place, and you have to because you want it in sorted order, you may have to shift a bunch of things. And if you want to insert at the beginning, you'll actually have to shift possibly b-1 things. So, so there's the log n as before, but then there's shifting, which costs order b. There's an array here of length b-1. You may have to shift everything. All right. And okay, so that's so what do we add all this up? We've got the find, we've got the plus b. But now, if you have an overflow, because you just filled this node, then you've got to split it. And what does splitting it involve? That involves creating a whole new array of size b. And not only that, I mean, you have to zero it out and you have to copy half of the things over. So that's another O of b. And so if you split, then there's another sort of O of b work that you have to do. And it's still not over because that split might have caused the parent to split, or might have overflowed the parent, in which case it has to split, and that might have overflowed this thing, so it might have to split, and so on. And so in the worst case, you get this thing here has to be multiplied by the height of the tree. And so you get log n plus b times, well, the height of the tree is log base b of n. That's not great. So this add operation takes log n plus b times log base b of n. That's not fantastic. And what about the number of IOs? So how many blocks or how many accesses to disk blocks do you have to do? Well, there's the log base b of n that you do during the search, and then maybe you have to walk back up the tree, splitting things, and each of those is creating a new block, right? So, you know, there's this block here that's getting split. That this one maybe could be the one that existed before, but you have to create a new one. That means you have to really go onto the disk and create that thing. So that's another, and that can happen this log base b of n times, but no worse than that. So we get again, the number of IOs, number of disk accesses is log base b of n. Okay. Good. So we're going to see about improving this shortly. But for now, let's leave the running time at that. And then there's finally the remove operation, which is no surprise. To remove something, if I want to remove x, well, there's maybe a small surprise. I go searching for x. And if I find x down in a leaf, that means it's living in some array down here. I just want to take it out of that array. If I find x earlier than that, so maybe if I find it up here, then what does that look like? Inside that node, I will see x. I want to get rid of it, but it's kind of awkward to get rid of things up in the middle of the tree like this. So what I'll do is go into this subtree and keep then taking the leftmost child, leftmost child, leftmost child, leftmost child until I get to a leaf. And so there's a leaf down here, and the first thing stored in that leaf is the thing that comes right after X in sorted order. And so I take that thing, use it to replace X, and then I'm back to the case of having to delete from a leaf, to remove from a leaf. So we saw a similar thing with certain kinds of binary search trees, where if you end up having to remove a node in the middle of the tree, you go into the right, take the smallest thing in the right subtree of that node to use that to replace it, and then you can remove that thing. The same thing happens here. So it always boils down to removing something from a leaf node. And of course, when you remove from a leaf node, most of the time it's okay, right? You have some things in your leaf node. One of them is X, the thing you want to remove. You remove it, that creates a gap, and you fill that in. But there's one problem, of course, which is if your leaf node looks like this, meaning that it has exactly b minus 1 values in it, then when I remove X, it's going to have b minus 2 values in it. And this thing says leaves have to store at least b minus 1 values. So then you have a situation at this thing that's called an underflow, meaning that it's not full enough. Okay. How do you deal with an underflow? Well, there's two things you can do. So this is a picture of these two things. If here's the node that just had an underflow because I removed some key from it, and that, look at that node's sibling. So it has something to the left or to the right of it, a child of the same parent, which comes immediately before or immediately after, and you try and borrow from that sibling if you can. So in this case, this one has the underflow. It needs one more key to make that underflow go away. This one has more keys than it strictly needs. Right? So it needed 2 keys, so that's b minus 1. It has 3, so it has 1 to lend this thing, but it doesn't really lend it. It actually gives it to the parent, and the parent gives this thing here. Right? So the borrow looks like the smallest key here goes up to the parent, and then to replace that key that separates these two, and then this one takes this one. So there's kind of a shuffle like this that happens. So that's what a borrow looks like. And if you borrow, then it's great. You're done. Right? If you're able to borrow, you stop there. Nothing changed in the parent in terms of the number of keys or children that it has, so you can stop. Sometimes, though, you can't borrow, and that's what's happening in this picture. This node has an underflow because you just removed something from it. This node already has the smallest number of keys it's allowed to have. It has b minus 1 keys, so I'm unable to borrow from it. Let's see. So there's b minus 2 keys over here. There's b minus 1 here, so this is less than you're allowed to have. This is exactly what you're allowed to have. And so I'll merge those two things. And again, it's worth paying attention to exactly what happens here. If I take b minus 1 keys and b minus 2 keys and b minus 1 keys, that should be 2b minus 3, right? But it's not. Well, I mean, it is. But there's an extra key that ends up going down in this merged node, and you see it here. So this is going to be 2b minus 2, because when I merge these things, the parent has one less child, which means it also needs to have one less key. And so in this example, you see the key 3 that was in the parent has to come down and live in this child. But there's room for it, because this one has b minus 2, this one has b minus 1. Add all that up, plus the extra key, there's only 2b minus 2. In fact, not only is there room for it, but there's a little space left at the end. All right. But if you end up having to do this merge, then notice the number of keys in the parent, or children of the parent, and keys in the parent went down, which means you need to check to see if it's now underflowing. And if it is, you either borrow or merge, you apply one of these two operations. And in the very worst case, what keeps happening is each time you do a merge, that causes the parent to underflow, which causes the parent to underflow, and so on, all the way up to the root. And that can take you from a root that looks like this, and then you do the merge, and you get a root that looks like this. It has no key in it, which means you can just get rid of it. And that's the way that the height of this tree goes down. Sometimes you end up removing something, which results in a whole series of merges, which go all the way up to the root, and now suddenly the root only has one child and no keys, which means it's not useful. You can just use its child as the new root. Okay, good. And if you think about the analysis of that, it's going to be all the same thing. There's a log n time to do that initial search, and then if you get really unlucky, you have to do all of these merges right from 2 leaves all the way up to the root. So that's the height of the tree, and each one of those involves taking 2 arrays, each of length roughly b, and compressing them into one array. So that's going to give you, again, this b log n. But the good news is, in terms of the number of IOs, that doesn't change things too. It's twice as many IOs, but not an outrageous increase. I mean, there are IOs that, I mean, you see that this thing is only working on, only has to touch 3 different nodes. And you may have to do that, the height of the tree number of times. So that gives you another, in terms of number of IOs, it's still on the order of log base b of n. Okay. All right. So this log base b of n, it turns out is the best you're going to be able to do for IOs. You can't. You won't be able to do better than that. There's a fairly easy argument, but it really comes down to anytime I inspect a node, like when I'm doing a search, for example, the node stores something like b keys, or 2b, I mean some constant times b keys, and whatever thing I'm searching for or adding or removing can only fit into sort of b or 2b plus 1 different ways into, there's only, it's not a binary decision unlike in a comparison of a single node, but it's not it's a degree b decision roughly. And that's where this log base b of n is coming from in the number of IOs. So that's unavoidable. That's the best you'll be able to do. But these are a bit disappointing. Log n plus b log n for the running time, right? So that means that if you were to compare this thing to a binary search tree, well, you know, this would be just in terms of the time you spend internally, it's gone up by a factor of b, so like a factor of 512. So 512 times slower than your typical binary search tree. So possibly O of B of the depth of that node. Well, it's actually, when you do a deletion, it is always, when you do an add or remove, it's always eventually something that changes at the leaf. So they all have the same, all the leaves have the same depth, h of t, but it's O of B times the, how many steps up you have to go before you get lucky and you don't have an underflow or an overflow. More in particular, in the case of removal, you get to borrow, or you don't have an underflow, and in the case of adding, you don't create an overflow. So we're actually going to prove now that it's not as bad as it looks. And here's the theorem, which is if I start with an empty B tree and perform any sequence of M add remove operations, then the total number of split and merge operations is at most 3m divided by 2. Okay. So now we get to the actually the cool part of this thing. So 3m divided by 2. Why? How does this happen? But what does it mean, first of all? So it says if I do a total of m add and remove operations, then the total number of splits is 3m divided by 2. And for us, these things in our analysis, they were slow because of the splits, right? So why b log n? Well, it's b log n if you get to this leaf and you have to split all the way back up to the root. Each time takes order b time. Why this? Well, because that happens if you remove from the leaf and then you have to merge all the way back up to the root. So this b log n all comes from the cost of splitting for add and merging for remove. And what this theorem is saying that is, yeah, okay, even though this can happen maybe once in a while that you end up having to go all the way to the root, on average, over the sequence of all m operations, it only happens, well, like 1.5 times per operation. So this is an overestimate, and so the theorem would then say that actually the running time for add and remove, if you ignore the cost of splitting and merging, is log n plus b. There's still a plus b because you have to mess around in one array at the bottom if you ignore the cost of splitting and merging. And then over the whole time, the total cost of splitting and merging is just another 3m times b. So the takeaway here is that actually this is log n plus b, and I'll say amortized. All right, so how would we do that? Well, we're going to use a proof technique that we've seen before. It's called the credit scheme. And we're going to give away at most 3 credits during each add or remove. So remember, this is this technique that you think of me giving every day my daughter $1. In this case, I give her $3. And then after 10 days, I can be certain that she has not bought more than $30 worth of stuff, because I only gave her a total of $30 in those 10 days. Even though I don't know exactly when she spent that money or whatever, I still know she couldn't have spent more than 30, because that's all I ever gave her. So in this scheme, we're going to give 3 credits each time we do an add and remove, and I'll show you where those go. And each split and merge is paid for with 2 credits. So I'll show you that if I only give away 3 each time I add and remove and put those in the right places, then each time I have to do a split or a merge, I'll be able to take 2 of those credits that I have saved, pay for that, those credits go away. And that is, in the example with my daughter, that's like saying I give her $3 a day, and a candy bar costs $2. So after 10 days, she has $30 saved up at most. Well, with $30, she could only have bought 15 candy bars. That's the 3m over 2. And you do this with these invariants. They're actually quite simple. There's 2 of them. If I have a node that's completely full, then it's going to be storing 3 credits. So every node that's completely full has to store 3 credits. It has to be ready for something. I mean, if it's completely full, it has to be ready to pay for a split. Okay. If I have a node that is, so this is a node with 2b minus 1 things. That's completely full. And if I have a node with b minus 1 things, then it needs to have a credit on it. It has to have 1 credit stored. Okay. So those are the rules. I'm going to keep this, and the other nodes I don't care. They don't need any credits. Okay. So that's the rules that I'll have to maintain, and then I'll show you that when I do that, so that I'm able to do these rules, and whenever merges and splits happen, I'll be able to find credits to pay for those things. So let's look, for example, at a split. Okay. All right, so a split happens when whatever operation I just did forced me to put something else in this node. And that caused the overflow. Well, if the thing that I just did caused the overflow, that means that the node before I did that was completely full. And this rule here says that if a node is completely full, it's storing 3 credits. Now, when I do the split, I have to pay for that. Well, there's where I get what did I say? You will pay with 2 credits. Yeah. So when I do the split, I have to pay for that. So that's going to use up 2 of my credits right away. I have to use those to pay for the split. That's what's happening here. And after the split, what do I have? That gives me these two nodes. Well, if I look at the credit invariant says if I have a node with b minus 1 things in it, I need to leave I need a credit on there. So this third credit, the one that was not used to pay for this split, has to go and live on this one because this thing has b minus 1 keys in it. All right, so that says a split I can do, and I can pay for that split. Now, let's think about the whole add operation. So how does an add operation look? Well, I said whenever I do one of these things, each add and remove, I give you 3 credits. Those are off to the side. And then, so I do the add, and maybe a split happens down here. But that's okay. This node, if it was split, we just argued that it's storing those 3 credits. It can pay 2 of those for the split and still keep 1 to deal with the fact that one of its nodes is light, is almost about to underflow. So I haven't used any of these 3 credits that you gave me yet. What am I going to do with them? Well, maybe there's a split, maybe, then I have to look at the parent. Maybe a split happens there, maybe a split happens there, and so on. But eventually, the splits stop happening. So you might think, well, there's 3 extra credits. What do I need those for? No, you do need those because look at where the splits stopped happening. So here there was a node that got split in 2. So that means its parent got an extra child, and maybe its parent was almost full. Right? Everything was occupied except for 1 spot, and then when I did this split, now that 1 spot is full. Credit invariant says I need to keep 3 credits on that node. Put 3 credits on that node because it's full now. Well, good thing I have those 3 credits that you gave me. So those I give to this node. The 3 credits that came with the operation are spent, but that's okay because the operation's over. I didn't have to split this node. All right, so that's how you do manage the credits during add. And during remove, let's look at what happens. During a remove, you give me 3 credits, and I do this search. I find this thing down here. Maybe a merge has to happen. So I remove something, and maybe that causes a merge. So, for instance, here's a merge. What the merge looks like. So why is a merge happening? Because this underflowed. Why did this underflow? Because I just removed something from it, and that caused the underflow. But that means that it had exactly b minus 1 things before that. So it was storing a credit by this rule. And this one was also storing a credit by the same rule. There's 2 credits. I take those away. I pay for the cost of the merge. And look at this node after the merge. It has 2b minus 2 things. It doesn't need to have any credits. And then, keep going up to the parent. And then finally, the same situation. When you do a remove, you have those 3 credits that I'm giving you at the beginning of the remove. Where are those going to go? Well, they're going to go to this, this unfortunate case that can happen when you, like when you borrow from something. Like, for instance, here, here's where you get away with borrowing. But when you got away with borrowing, this thing became, it went from being in a good state to this state where it needs a credit. So you use one of your 3 credits to give to this thing. Or possibly you do a merge, and what happens, nothing exciting happens at the parent except that the number of children goes down, in which case it might reach that b minus 2 state. So you give it a credit. All right, so with the 3 credits you give me during add and remove, I can maintain these credit invariants. If I have the credit invariants, I can pay for 2 credits for every split and merge. So the conclusion is that if you do only M operations, you only get 3M over 2 splits or merges in total. So in fact, you may have noticed there's a bit of asymmetry here. When I do the remove, I didn't actually need all 3 credits because the remove only makes things like this, and actually it can only make one thing like this that wasn't there before. So actually on the remove you'd only have to give out 1 credit, but then you get a more complicated statement of this thing that says if I do this many adds and this many removes, then the total number of splits and merges is at most something else. This is just a simpler statement. But yeah, the removes are actually less expensive than the adds. Okay, and that is it. We are out of time. That's the class for today, and actually that's the class for this semester. Enjoy your weekend, and come see me in office hours if you have any questions. I can try and answer them for you. All right. Thank you.